Okay, so this week we're going to be talking about the electron transport chain and chemiosmotic theory. Um, I'm going to be making kind of an introductory video to begin with, just to go over um, kind of some of like the bigger picture idea here, because we've covered quite a bit of material with glycolysis, pyruvate dehydrogenase, and the Tca cycle up to now. And I want you guys, I think, understanding the bigger picture will help you whenever you're trying to understand like the little picture details as we go through the electron transport chain. Okay, so I'm gonna kind of go over like the backgrounds a little bit and how the electron transport chain helps us make ATP, and then we'll in a future video we'll talk about like the specific complexes of the electron transport chain, like complex 1, 2, 3, and 4, ATP synthase, and also maybe like uncouplers and stuff like that. Okay, but this right now what we're going to do is we're going to look at everything, from like like the bigger picture view. And the idea here, and I kind of picked this cartoon. I don't know why I picked this cartoon, to be honest, but I just wanted a picture where, again, where the idea here is that, in order for us to live, we need to consume food. So right over here, this cartoon character Homer, he's eating a donut, and the goal, again, at the end of the day is, so when we consume this, we not only do we need nutrients, but we also kind of need energy in the form of ATP, so that we can continue to process and continue to function and continue to do a lot of biological functions which require ATP. And if we didn't have ATP, we would no longer continue to live. Okay, so I want you to have this idea in the back of your mind that our entire goal through like all of glycolysis, the Tca cycle, and the electron transport chain, our end goal is to make ATP. Okay, and if you look at it right now, so we've already covered glycolysis, and glycolysis, again, just the summary is that we're going from glucose to 2 pyruvate molecules, and we're going to be oxidizing glucose. And in the process of doing this, as we're breaking down glucose, we're going to make 2 NADH, 2 ATP. And okay, so this is very good if we're thinking back to our bigger picture goal of making ATP. We're making 2 ATP here. We're also making this NADH molecule, 2 NADH molecules, which are our electron carriers, right? So as we're oxidizing the carbons in glucose, we're going to be storing some of those electrons. Okay, remember, oxidation is loss of electrons. We're going to be storing some of those electrons from NAD plus. They're going to go, maybe if I, okay. They're going to go from NAD plus into, or 2 NAD plus, and then I guess you can do 2 ADP. It's okay. We're going to go from 2 NAD plus, and we're going to reduce them into NADH. Okay, so the NAD plus are going to accept our electrons, be reduced into NADH. Okay, and we kind of glanced over what we're going to do with the NADH. We said we're going to come back to it later, and this is the whole point of the video, is to show you how everything connects. But okay, so we made 2 NADH in glycolysis, and now this pyruvate molecule, what it's going to do is it's going to undergo more breakdown through PDH and the Tca cycle. And I just wanted to add one detail, is that I know in our class we directly went from pyruvate to PDH and to the Tca cycle, and we didn't really talk about the mitochondria until this week. But just so that you are aware, you see all these mitochondria that I circled right over here. So as soon as we form pyruvate, these pyruvate molecules are going to actually be transported into the mitochondria. So this is just a zoom in of the mitochondria. Okay, so we have a bunch of different mitochondria in our cells. So glycolysis is happening like, in the cytosol. So glycolysis, we have our enzymes right over here, and we undergo glycolysis in the cytosol. And the idea here is, okay, we form pyruvate, and now the pyruvate molecules, they're going to go into our mitochondria. Okay, so it's going to come into our mitochondria. The mitochondria has 2 membranes. It has an inner membrane and an outer membrane. So it first crosses through the outer membrane through porins, and then it has a transporter on the inner membrane, and it comes into the mitochondrial matrix. Okay, so notice, so the matrix is like the most inner part of our mitochondria. So I'm kind of going to shade it in right here. Okay, so our pyruvate molecule is going to come into here, and this is actually where PDH, the Tca cycle, and all these things occur. Even though we didn't really talk about the mitochondria until this week, I just wanted to point this out, that again, when we talk about the Tca cycle, PDH, all these things are actually happening inside the matrix of the mitochondria. Okay, so glycolysis happens in the cytosol. everything else, PDH and the Tca cycle happens inside of the matrix of the mitochondria. Okay, so it has to pass through those two membranes of the mitochondria. It comes into the matrix. Okay, so now again, we're going to go through PDH, and you have E1, E2, and E3, and your E1 facilitates a decarboxylation, and E3 forms NADH. So again, we made another NADH, which is another electron carrier, which is very good. So now we're making a lot of NADH, not so much ATP, which again, that was our goal. So let's just keep going. And now we're going to go to the Tca cycle. So our substrate for the Tca cycle again is acetyl-CoA combines with oxaloacetate to form citrate, and we go through the Tca cycle. And in the process of the Tca cycle, you're going to form 3 NADHs, you're going to form a GTP, and you're going to form an FADH2. Now, you're going to say, well, okay, remember, our big picture goal when this cartoon character was having his donut was to make ATP, but up to now, we didn't really make ATP. We kind of just made more NADH and very few ATP. So this is where the electron transport chain comes in, is now all that work we did, all that work to break down glucose into pyruvate, all that work we did in the Tca cycle to further oxidize our carbons and harness those energy or store those energies in those electron carriers of NADH and FADH2. Now we're going to get into our payoff. We're going to take that energy and we're going to finally make our end goal of ATP. Okay, so again, this picture is a little bit off. The Tca cycle is like occurring inside the matrix. So this is the mitochondrial matrix. So again, this Tca cycle is kind of, again, occurring in the matrix. Okay, and same thing with PDH. They're both occurring in the matrix of the mitochondria. And then on the membrane of the mitochondria, so remember we said that the mitochondria had an outer membrane, or had two membranes, the outer membrane and an inner membrane. So on the inner membrane, you're going to have this thing called an electron transport chain. And as its name implies, okay, so all we're going to be doing is we're going to be transporting the electrons, right? Remember, we said that we're oxidizing carbons and we store that energy or those electrons in the form of NADH and FADH2. We're going to just be oxidizing NADH back into NAD+, and then we're going to take those electrons, and you can kind of see that they're following like this path through the complexes, okay? They're going to pass through complex 1, then coenzyme Q, complex 3, cytochrome C, complex 4, which we'll talk about in more detail in a future video. But again, we're just going to, the electron transport chain is just passing those electrons through the complexes, and the ultimate electron acceptor is going to be oxygen. So if you didn't have oxygen, everything else would get held up. But we're going to then pass those electrons to oxygen, reduce it into water, okay? So oxygen is going to be reduced to water. And as we're doing this, we're also going to be doing something else, okay? And what you guys should just take away from this is, okay, the electron transport chain, what it's doing is it's pumping protons from the mitochondrial matrix. So all the protons that are here, we're just pumping it into the inner membrane space. So we're basically, if we correlate it back to this picture that we had over here, well, that was very good. All we're doing is we're taking those protons that are in the matrix, or the inside of like the red region, and then we're just pumping them into the IMS, so that region between the two membranes, okay? So we're effectively creating this concentration gradient in the inner membrane space, okay? So let's just go back over here and just go over a few things. So again, what we're doing is we're taking those electrons from the electron carriers from the Tca cycle and even glycolysis, okay? We're taking those electrons and we're going to be passing them through the different complexes of the electron transport chain. So through the inner membrane, we're going to be passing these electrons. And as we're passing those electrons, we're going to use that energy. We're going to use that energy. Somehow we're making energy, and we're going to eventually make ATP using that energy, okay? Now, the way that this works, and this is where the idea of chemiosmotic theory comes in, okay? The way that this works is, up to 1961, scientists didn't really know how we went exactly from NADH to ATP. They knew that the electron transport chain and ATP synthase were near each other and they were somehow connected, but they couldn't figure out exactly what was connecting the two together, okay? And it wasn't until Dr. Mitchell, I think his name was Dr. Mitchell, Dr. Mitchell came along and he did a bunch of experiments, which you'll see in your which you'll see in lecture, and the study questions show you like some experimental details which support his theory. But the idea here is that Dr. Mitchell in 1961, he came up with the idea that this idea of chemiosmotic theory, where the electron transport chain is coupled to ATP synthase by this idea of a pH gradient, okay? So he thought, Dr. Mitchell thought that the way that the electron transport chain is connected to ATP synthase, or the way that we go from NADH to finally making ATP, is through a proton gradient, okay? And at the time, his idea was actually very radical, and his idea, I don't think, was accepted until I think the mid or late 70s. I think it was like it was somewhere in like the late 70s where he finally won like the Nobel Prize, only like 15 years after he thought of this idea, okay? So it had to be experimentally verified, and it was very radical at the time. But now that it's kind of, you know, he won the Nobel Prize, you kind of want to understand, well, what's going on and how are the two connected? And the way that it's connected, again, is by this pH gradient, or this electrochemical gradient, and this is how it works, okay? So what we're doing is, again, up to now, what we did is we made a bunch of NADH and FADH2 molecules, and our end goal, again, is to make ATP, which we haven't done thus far, or very minimally we've done up to now. Now what we want to do is we're going to be oxidizing this NADH, okay? We're going to oxidize this NADH, and we're going to take those electrons and pass it through, again, the electron transport chain. Now, as we're passing those electrons through the electron transport chain, I want you guys to think about it like this. When you have electrons moving, right? If in our physics class we learned that when electrons move, you're creating a current, right? And you can think of it, another way to like visualize the electron transport chain, it's kind of like a mini battery, okay? So we're moving these electrons across the complexes, and we're creating this current, and we're going to use this current to power an unfavorable process, okay? So you could think of it like a car. A car by itself, it just wants to stay stuck. It doesn't want to really move. But whenever you have a battery, and this is like an electric vehicle, I guess, whenever you have a battery, it'll help the car do something unfavorable, which is finally move it. If you're going to use the energy from the battery to move it. Same thing happens with the electron transport chain, okay? Normally, what you want to do is, you know, the universe tends to disorder. You like, for example, if we had like a cup of water right over here, right? Or a cup of water, and we added like some kind of dye or something, the dye is going to spread out, and it's going to basically increase the disorder. The whole idea here is that we're always trying to increase the disorder. But what we're technically doing over here is we're pumping these protons. So as we're transferring those electrons, we're doing something unfavorable and pumping these protons into the IMS, and we're kind of creating this order, right? So again, the electron transport chain is pumping these protons against this concentration gradient. So it's basically creating order, because we're pumping all the protons as much as we can into the inner membrane space, or into the IMS, okay? And this is something that's naturally unfavorable, because if you go back to week 2, we had this formula, right? Oops. We had this formula, delta G equals delta H minus T delta S, right? And we always said that we wanted to increase the entropy, right? But over here, what are we doing? We're actually decreasing the entropy. We're putting all of our protons in one place, and we're kind of creating a concentration gradient. So the idea here is that the whole idea here is that you need the energy of those electrons, and as we're passing those electrons through the complexes, we're creating this current, and we're using that current to power these proton wires and other things, and we're going to be pumping protons from the mitochondrial matrix against this concentration gradient into the inner membrane space, okay? Now, exactly how this does this, we'll talk in a future video, but that's the idea I want you guys to take away from this. The electron transport chain is going to pump protons from the matrix against this concentration gradient into the IMS, where there's a higher concentration of protons in the IMS, okay? Now what's going to happen is ATP synthase is going to take that proton gradient, and it's going to eventually make ATP, okay? So the idea here is it's going to harness that electrochemical gradient, or that energy in the electrochemical gradient, because technically, if you think about it, now the protons really want to go back and go with their concentration gradient back into the matrix. So ATP synthase dissipates that proton gradient, and by dissipating that proton gradient, it powers its own self, so that you can convert ADP and PI into ATP. And we'll talk about exactly how this occurs in class, and I'll maybe make a future video on it. but that's the idea, okay? So the main idea here is that the electron transport chain is coupled to ATP synthase by a pH gradient or an H plus gradient, right? And then the electron transport chain produces the pH gradient that the ATP synthase requires for function. So we're basically pumping these protons into the IMS, and then the ATP synthase requires that proton gradient in order for it to function. So if we didn't have the electron transport chain functioning, and if we didn't have a proton gradient, ATP synthase would not work, because ATP synthase requires that electrochemical gradient, and it uses that electrochemical gradient to form ATP. Okay, so these are these first 2 points. Now, the last point, and this is, I think, really key in the worksheet and why a lot of students get a little bit confused, and I think this is one of the key points that you should take away from the worksheet, is that the reciprocal is also true, in that ATP synthase dissipates the proton gradient, allowing the ETC to continue to function. So this is this key idea that not a lot of students catch on in the beginning, okay? So a lot of students, they understand, yes, the electron transport chain, we're gonna pump protons against the concentration gradient into the IMS, creating this electrochemical gradient. ATP synthase will then harness the electrochemical gradient to form ATP, and that's fine and dandy for most students. This last idea over here is a key idea that a lot of students don't pick up on, is that ATP synthase, yes, it's dissipating our proton gradient, but as it's dissipating our proton gradient, it's allowing the ETC to continue to function. And the way that this works, and the way that you can think about it, is like this. Well, we just said that, as we're pumping these protons against the concentration gradient, it's unfavorable. We just said that we're decreasing. So we want to increase the entropy, but by pumping the protons against this concentration gradient, we're actually increasing the order, or what we're doing is we're decreasing the entropy as we pump more protons against the concentration gradient, right? So that's what we're doing. And you could think of it that, okay, so how are we going to do that? Or how are we going to power this unfavorable process? Is we're going to pass these electrons through the complexes, and that's what helps power helps pump these protons against their concentration gradient. But think about it like this. If we said that ATP synthase no longer functions, so if we say that this no longer functions, well, is there anything to dissipate the proton gradient? No, there isn't, right? So what's going to happen is, first, it's going to be fine. We're going to keep pumping protons. These complexes are going to keep pumping protons and pumping protons. And as long as their delta G is negative, it's going to be favorable. But then after a certain point, what's going to end up happening is that the delta G associated with pumping the protons, because now we're increasing the order so much, the delta S is going to decrease so much that it's going to become, the delta G overall is going to become positive, okay? So the idea here is that, yes, it's favorable in the beginning, and as long as we keep dissipating that proton gradient, everything's fine and dandy, and we can continue to have the electron transport chain continue to function and pump protons. But if we hindered ATP synthase, if we inhibited that, ATP synthase would no longer be able to dissipate that proton gradient, meaning that all these protons would build up in the inner membrane space, and then eventually, because we're increasing the order so much, it would become actually unfavorable to continue to pump protons against the concentration gradient, and then the electron transport chain would shut down as well. Okay, so putting everything together as a resummary, okay, so electron transport chain is coupled to ATP synthase by a pH gradient or an H plus gradient. As we're oxidizing these electron carriers, and we'll talk about exactly where succinate and fumarate come from, but it's going to be from the Tca cycle, but we'll talk about this more in a future video. But again, we're going to take the energy from those electrons, we're going to pass them through the complexes. By doing this, we're going to create a current, and we're going to use that current or the battery to pump protons from the mitochondrial matrix into the inner membrane space, which is something that is unfavorable, but because again, we're pumping those electrons, what we're doing is passing those electrons, it's going to power that process, and it's going to have a negative delta G. Okay, so we're gonna create an electrochemical gradient as we're transferring those electrons between the complexes, and then what ATP synthase is going to do, it's going to harness that electrochemical gradient, converting that electrochemical gradient into mechanical energy and then into chemical energy in the form of ATP. But the idea here is that ATP synthase will then convert this electrochemical gradient. It'll take some of these protons, it'll bring it through its complex, and then we will then make ATP. Okay, And then, so again, ETC will produce the pH gradient that ATP synthase requires for it to function, okay? So again, if we inhibited ETC, we won't create that proton gradient, so then ATP synthase will not function because it doesn't have a proton gradient. Then the converse is also, or the inverse is also true, or the reciprocal is also true, that ATP synthase is continually dissipating that proton gradient, allowing the ETC to continue to function. And if we didn't have ATP synthase, we wouldn't be able to dissipate that proton gradient. If we're not able to dissipate that proton gradient, it will become, after a while, it will become unfavorable for the electron transport chain to continue to pump protons against its concentration gradient, because there's going to be a buildup of protons in the IMS. And because of this, the electron transport chain would also shut down. So the idea here is that the electron transport chain needs ATP synthase, and ATP synthase needs the electron transport chain in order to function. Obviously, there's going to be a few exceptions when we'll talk about inhibitors and uncouplers and stuff like that. But this is the main idea here, is that they're coupled together by pH gradient. And again, our goal was to make ATP. And now we saw that we're going to take those NADH molecules made in glycolysis, and same thing with the Tca cycle and PDH. And what we're doing is, and same thing for FADH2, we're going to take them into the complexes of the electron transport chain and ultimately create ATP, which was our goal, and that's why we can continue to live.